We can summarize our investigation of hydrostatics with the items in this tactics box from your textbook. When you start, you should always start with a picture because you need to identify where the open surfaces are, where the pistons are, any sort of boundaries, and any other features that might affect pressure. Include your knowns and unknowns, like the density of the fluid or the height or area of particular items. And take a close look and identify places where you either need to find the pressure or where you already know the pressure. And then utilize our horizontal lines. So we can find the pressure at various surfaces using some of the equations that we've derived throughout this video series. If the surface is open to the air, you can assume that it's at atmospheric pressure, which would be 1 atmosphere, unless you're told specifically otherwise. If your surface is covered by a different gas, then that pressure is going to be whatever the pressure of the gas is. And if you've got a closed surface, then it's going to be whatever the force of the surface is, divided by the area of that surface. Again, horizontal lines are your friend, because if the fluid is connected, then the pressure is going to be the same at every horizontal point. Make sure that you know whether the pressure numbers that you've been given are gauge pressure numbers or absolute pressure numbers. There's a difference of 1 atmosphere between the two. And then finally, use your hydrostatic pressure equation that we've derived multiple times. If you forget it, you can always go through and rederive it just by looking at your net forces. So let's go through and take a look at how hydraulics are a good summary for everything that we've learned so far. Hydraulics are used to move large or massive items up or down with less force. So you have used hydraulics in lots of systems before. Some examples are the brake system in your car or in your bicycle, and the hydraulic lifts that we're going to take a look at right now. And all of this is based on Pascal's principle. If you increase the pressure at one point in a liquid, say by pushing a piston in, like what we've got marked here as F1, that pressure increase is transmitted to all points in the fluid. That means that the second piston, if it's movable, will move up. That's the F2 area that we've got there with the car. If you push down on F1, the car will move up. And that's because of that pressure being transmitted to all points of the liquid. And hydraulics allow you to go through and do useful work. So let's examine the system that we have here. We've got points 1 and 2 marked. Point 1 is on the left side, right at where that small piston is. So the pressure at point 1 is going to be equal to the atmospheric pressure, P0, plus the force F1 that's being applied divided by the area A1 of the piston itself. Similarly, over at point 2, we'll have the atmospheric pressure plus the force F2, which is mostly due to the weight of the car, divided by the area of the second piston, plus the density of the liquid, G, and the height of the liquid above point 2. Since point 1 and point 2 are along a horizontal line, those pressures need to be equal. So if we set those equal, we can go through and derive the amount of force, F1, needed to keep this system in equilibrium. Notice that the atmospheric pressures cancel because the atmosphere is pushing down on both pistons equally. To determine that force F1, we multiply through by our area A1. And we find that the force needed to keep this system in equilibrium is equal to F2 times the ratio of area 1 to area 2 plus rho GH area 1. So this is what's needed to keep it in equilibrium so that the car doesn't fall back down. If we remove that force on piston 1, then the car will fall down. Now what if we want to push the car higher up? If we want to do that, we'll need to increase the force of F1 to push the car up higher. If we want the car to fall down, then we decrease the force on F1. So let's take a closer look at exactly how much we need to go through and move that piston marked 1 in order to push the car up a certain amount. Now, because the fluid is incompressible, if we push that piston down, we're displacing a certain volume of this liquid. That means that the second piston is going to rise up by the same volume. Now, our volume 1 on the left-hand side is equal to the area 1 times the distance we push it down. On the right-hand side, the second piston is going to rise up. Again, that volume is area 2, the surface area of that piston, times the distance d2 that it rises up. These two volumes are equal, so we can go through, do our algebra, and determine that the car will rise up a distance d2, which is equal to the distance that you push down on the left-hand side on piston 1, times the ratio of the areas between the two, A1 over A2. So hydraulics are sometimes called force multipliers because you do a little bit on one side and its effect is multiplied on the other side. Let's go through and look at an example with some numbers before we finish out this video. The hydraulic lift at a car repair shop is filled with oil. The car rests on a 25 centimeter diameter piston. To lift the car, compressed air is used to push down on a 6 centimeter diameter piston. What does the pressure gauge read when a 1,300 kilogram car is 2.0 meters above the compressed air piston? So let's start with looking at what our knowns are. So our car, which we've been calling point 2 or related to point 2, has a radius of 12.5 centimeters. We know that our lift is filled with oil, so we can use our table to look up the density of oil. That's 900 kilograms per meter cubed. We know that our first piston is only a 6 centimeter diameter, which means a R1 of 3 centimeters. That's the one we're going to push down on. And we want to raise the car a distance of 2 meters. And we want to figure out what the pressure gauge reads when the car is 2 meters up. So let's first start with calculating our areas. We'll need both of them. So area of piston 1 is pi times R1 squared, which is 0.00283 meters squared. Converted those centimeters to meters first. Area of piston 2, pi R2 squared, is 0.0491 meters squared. And that makes sense because that's the larger of our two pistons. Now the force 2 is just due to the force of the car, so that's mg. And again, our height is 2.0 meters. So our question is asking about what the pressure gauge is going to read. So we're specifically looking for what P1 is. So P1, the pressure at that point, is going to be due to the force F1 divided by A1, the surface area. And that's going to equal the same pressure at point 2, which is F2 over A2 plus rho GH, where H is that height of the liquid. So we said before that F2 is just the force of our car, so that's mg. We'll plug that in for F2 and rewrite our equation. And at this point, we have all the numbers we need to go through and calculate what this is. So our end result is 2.76 times 10 to the 5 pascals, which is equivalent to 2.7 atmospheres. Now this pressure is the gauge pressure, exactly what we were asked to find, because we did not include P0 anywhere in our analysis. If we wanted to know what the absolute pressure is at point 1, then it would be 3.7 atmospheres, because again, absolute pressure is 1 atmosphere higher than gauge pressure.